Hello everyone, welcome back to my channel. It's now 2004 and I want to say Happy New Year for all of you. Wish you more success this year. This is my first video in 2004 and in this video we'll discuss about 5G international roaming, the definition, the specification and the requirements, what network elements involved in this 5G international roaming, how is the workflow, and the implementation using the security edge protection proxy node and service communication proxy node. Let's check it out. The 5G international roaming is the ability of mobile subscribers to use the 5G service while they are outside their home country. To use this 5G international roaming service, both network operators in their home country and the destination country must be able to provide the 5G service. There is also a requirement that these two operators in these two countries has an agreed roaming partnership both in technical and commercial areas to be able to implement the seamless 5G services between two countries. And the user or the mobile subscriber already purchased the roaming package into the destination countries and has sufficient credits to use the service. So what needs to be agreed between two mobile network operators to establish the roaming partnership? The first one is the roaming agreement document. This is the primary document that outlines the terms and conditions of the roaming relationship. It covers aspects such as technical requirements, financial settlements, and the legal obligations. The agreement defines how the networks will interoperate and the services that will be provided. The second document is the Service Level Agreement or SLA. This document specifies the quality of services that the roaming partner is expected to provide. It includes parameters such as network performance, availability, reliability, and customer support standards. SLAs help ensure a consistent and acceptable level of service for roaming subscribers. The third one is the interconnection agreement. This document addresses the technical details of how the networks will interconnect to facilitate roaming. It covers issues such as signaling protocols, data exchange formats, and the network interfaces required for seamless communication between the home and visited networks. The next one is the billing and settlements agreement. Roaming involves financial transaction between home and visited networks. The billing and settlement agreements outlines how charges will be calculated, exchanged, and settled between the operators. It also defines the financial aspects of the roaming relationship, including wholesale rates and revenue sharing. The next one is the security agreement document. To ensure the security and the integrity of the roaming services, mobile network operators establish security agreements. This document outlines measures to protect the networks and subscribers from potential security threats, fraud, and unauthorized access. The next one is the regulatory compliance documents. Operators need to ensure that their roaming agreement complies with local and international regulations. This may include documents demonstrating compliance with telecommunication laws, data protection regulations, and other relevant legal requirements. Next is technical specification document. Detailed technical specifications may be provided to ensure compatibility between the networks. This can include information on supported technologies, frequency bands, and network configuration. The last one is the dispute resolution mechanisms document. In case of disputes or disagreements between the two mobile network operators, a dispute resolution mechanism is often included in the roaming agreement. This outlines the steps and processes for resolving conflicts in a fair and timely manner. So how is the 5G roaming interconnection works between two mobile network operators in two countries? For example, here we have two mobile network operators in two countries. The first one is in Indonesia. We have the mobile network operator which has MCC or mobile country code 510 and mobile network code 01, which is Indosat operator. And in Japan, we have the mobile country code 440 and mobile network code 11, which is belong to the Rakuten Mobile or NTT Docomo. So traditionally, we have the 3G roaming and 4G roaming interconnection, where in the 3G interconnection for roaming, we have the connection between the two mobile network operators where the network edge of each network operator is the ISTP and STP or signaling transfer point is interconnected with the roaming exchange. And in 4G, we have the diameter routing agent and diameter edge agent in the edge of each network interconnected with the roaming exchange. In 5G, we have the network node called the SCP and SAPP or Security Edge Protection Proxy and Service Connection Proxy, which is interconnected via the roaming intermediaries, in this case IPX, or it could be also the roaming hub operators. So the communication here is via HTTP2 protocols, where the roaming subscribers in the visited PLMN will be interrogated to its home 5G network using this interconnection between SAPP in the two countries. Whenever it needs to interrogate the subscriber data, it will communicate via this connection to the designated network elements in the home PLMN. So what is the Secure Edge Protection Proxy is? The SEPP, or the Secure Edge Protection Proxy, is the network element which has the main function to protect the mobile network as it sits at the edge of the mobile network, and it acts as interconnection proxy between two mobile network operators. It has the main function as gating, policing, and topology hiding. Gating means that it will ensure that only the correct message is exchanged between mobile network operators. And the second one is policing, which will ensure that no malicious network messages will enter the mobile network. And also topology hiding, which will ensure that no sensitive information is exchanged between mobile networks operators. The SEPP between the two mobile network operators is connected via the N32 interface, which consists of N32C for the control plane and N32F for the data plane. The further discussion of the SEPP specification we can find in the GSMR roaming guideline and the 3GPP technical specification 29.573 about the 5G system element interconnection. Now let's talk about the Service Communication Proxy, or SCP. The SCP, or Service Communication Proxy, plays an important role in the 5G core networks deployment. It acts like a switch or a signaling aggregator between network functions, since it will interconnect the signaling message between network functions. It plays an important role for simplifying the interconnection or topology, so it will reduce the total cost of 5G network core deployment. It is also acts as a single point of signaling load observation and performance, so we can decide whether we have to scale up or scale down the SCP's deployment based on the network signaling load and performance. If we compare the SCP communication model D to other communication models, the model D is more efficient in terms of the number of routings between network functions, because the SCP will act as a termination point of the signaling routing from each signaling network functions. It will also reduce the load of the network routing in the network registration functions, since the NRF will only connect to the SCP for doing its tests in network function registration and network service discovery. Now let's discuss about the 5G roaming architecture model. There are two models that we can deploy for the 5G international roaming. The first one is the local breakout, and the second one is the home routed. In the local breakout, the convert charging is happening on the visited PLMN site, while in the home routed, the convert charging is happening in the home PLMN site. So in the local breakout, the visited PLMN only interrogate the home PLMN for the authentication process and also to query the subscriber data in the UDM and UDR. While in the home routed, it will send the request from the visited PLMN to the home PLMN for the connection to the data network itself. So in the home routed, it will only connect the cord to the radio sites and create the session for the 5G session to the UPF for data, but this UPF in the visited PLMN will then forward the request to the UPF or user preference function in the home PLMN. So the charging will be controlled by the home network in the home routed model. While in local breakout, the charging is controlled in the visited PLMN. But for the policy, the visited PLMN may contact the PCF in the home PLMN to apply the policy which is applied in the home PLMN PCF. And the charging itself and the billing will be done in the visited PLMN. Okay, we will simulate the 5G data roaming registration using the Open5GS software simulator. But before that, we will review first what messages are involved in the data roaming registration workflow. In this case, we will use the local breakout model for this data roaming registration, and it will involve several nodes in the several network function in the visited PLMN and the home PLMN. In the visited PLMN, we have the UE and the G node B. Also, we have the access and mobility function, this service communication proxy, the policy charging function, the session management function, the secure edge protection proxy function. In the home pay element side, we have the SEPP or secure edge protection proxy, the SCP, the authentication server function, the unified data management, and the unified data repository. This workflow starts in the visited PLMN when the UE send the registration request to the AMF. The AMF will then reply back with the identity request, and the UE will reply with the identity response. The identity here sent will be the subscriber unique-seal identity, which then be checked by the AMF to the authentication server function. The AMF will send the request to get the authentication factor from the authentication server function. Once received this message, the SCP of the visited PLMN will send to the SEPP of the visited PLMN, and then SEPP of the visited PLMN will send to the SEPP of the home PLMN via the IPX. The message then will be sent to to the SCP of the home PLMN, which then be routed to the authentication server function. The authentication server function will need to perform the query to the unified data management to get the authentication factor, and the unified data management will send the request to unified data repository. The unified data repository will send the data for this authentication back to the UDM. UDM will send back to the authentication server function. The authentication server function will route back this message to the AMF in the visited PLMN via the home SCP, home SEPP, the IPX, visited SEPP, the visited SCP, and then received by the visited AMF. Once received this authentication factor, AMF will send authentication requests containing the random and authentication number to the UE, and UE will respond with the rest variable to the AMF. This rest value will be checked again by the AMF to the authentication server function in the home PLMN via the same route as previous request. And then the authentication server function will forward this message to the UDM, and the UDM will forward this message to the UDR. The UDR will check this rest value. Once it's okay, it will send the authentication success back to the UDM, and the UDM will send back to the authentication server function, which will route it back again to the AMF in the visited PLMN. After this message received, the AMF will send the next message is the security mode command and replied by the UE by the G0B with security mode complete. And then the AMF will prepare for the context creation, and it will need the subscriber data to the UDM. It will send first the registration for the 3GPP access for the subscriber to UDM. Once okay, and then it will send another request for the access mobility data to the UDM, and UDM of the home PLMN will send the access mobility data such as UE AMBR. It will also send the subscriber data management data request for the SMF selection. Once it's confirmed from the UDM, it will also send the request to the policy charging function to the PCF, and PCF will reply with the PCF rule applied in the context creation. Once received, the AMF will send initial context setup request to the UE, and then the UE will reply back with the context setup response. And once this received, the AMF will send the context modification request to the SMF. Once received this message, SMF will send the query to the UDM for the subscriber data, particularly for this request. It will send the request to the UDM for this context creation, and then UDM will reply back. UDM in the home element will reply back with the subscriber profile containing QoS profile, AMBR, and other data to the UDM will query the subscriber data to the UDR, and the UDR will send back the subscriber data to the UDM, which then be sent back to the SMF. Once received this message, SMF will then query to the PCF, the policy, the rule ID will be applied for this session, and then Once receive the rule ID, it will send the confirmation to the AMF, which then send the PDU session resource setup request to the UE and responded by the UE with PDU session resource setup response. Okay, now let's try to simulate this 5G international data roaming registration workflow using the Open 5GS software. How we can simulate this using Open 5GS is available on the Open 5GS website. How to install the Open 5GS for roaming, and then the host setting, and also the NF setting for each network functions available on this address. Okay, now let's start to see the configuration of our 5G cluster. We have here the list of created pods to be able to support this registration tests. Let's have a look in the Red Hat OpenShift console. I have set the topology of these 5G Kubernetes pods, and you can see here we have pods for the visited PLMN at the left side and pods for the home PLMN at the right side. We have the SCP pods here as the central of interconnection between network functions pods or the signaling pods, and between PLMN, between visited and home PLMN, it was connected with the SEPP pods from each PLMN. As we can see in this data roaming workflow, registration workflow, we have the mandatory network function for this registration workflow scenario using the local breakout. In the visited PLMN, we must have the UE run nodes pods, PMF pods, SCP, PCF, SMF, and SEPP pods. On the other hand, in the home PLMN, we must have the SEPP pod, SCP pod, the authentication server function, the UDM, and the UDR pod. This is the minimum pod requirements to be able to do this simulation. Okay, the first one is the AMF pod in the visited PLMN. We have here the AMF 44011. Let's try to access it. Let's see the configuration. We have here the AMF configuration for the visited PLMN. The SPA interface, and the client is the SCP. So here the SCP is the gateway for the signaling of this AMF to other network function. And then the other configuration is for NGAP, the access control. We have two PLMN here. First one is the visited PLMN, and second one is the home PLMN. And other related configuration for the access. Okay, the next one is the SCP. Of visited PLMN. If we see the configuration, of this SCP, it contains the SBI server interface and also connection to the NRF. Since we have the NRF for the network registration and network discovery, and the SCP will work on behalf of this NRF. You can see here the mapping for this NRF in the host file. The next one is we would like to see the TCF. This is the PCF configuration for the visited PLMN. We have here the configuration for the interface. Have the SCP as the gateway. And also here we have the policy configuration for the home PLMN slice. We want to see also the SEPP configuration of the visited PLMN. Here we have the configuration for the SBI interface using the domain name and also the IP of the STP connection, URI connection. We have also the configuration for N32 interface. And here, this SCP will act as the sender. And the client is the SEPP node at the home PLMN. The similar config also applied in the SCPP of the home PLMN. Yeah, we have here the similar configuration, but the server here is the SEPP of the home PLMN, and the client is the SEPP of the visited PLMN. We have also the authentication server function, UDM and UDR for this home PLMN. Let's quickly check configuration. We have the SBA interface setting using the domain name and also connection to SCP. Also for the UDM of the home PLMN, we have here the keys for the home PLMN, also the SPA setting and the address of the SCP. And the last one is the UDR of the home PLMN. There is a configuration to access the MongoDB database for the subscriber database, and also SBI address and the SCP address. Okay, now let's simulate this registration test for this 5G roaming. We'll expect that this workflow will correctly work, and we want to see the network elements or network function involved in this inter-PLMN communication between the visited PLMN and the home PLMN. So for the sample here, we want to see in the traces the call flow for this authentication, UE authentication data requests from the access mobility function in the visited PLMN to the authentication server function in the home PLMN, which is Indosat PLMN. Okay, before we start the test script, we would like to set the trace in the we will set the trace in the AMF of the visited PLMN, in the SCP of visited PLMN, the SEPP of the visited PLMN, the SEPP and the SCP of the home PLMN also, to see what message is going in and out in this network function. First, we would like to set a trace in the AMF of the visited PLMN. The namespace is 5GNet. The second trace will be for the SCP of the visited PLMN. The third one, we would like to see the message in the SEPP of the home PLMN. Actually, we can set both in the SEPP on the home PLMN and visited PLMN, but since the trace in the visited PLMN already represented by the trace of the SCP, so we can just set the trace for the SEPP of the home PLMN. And the last one is the trace for the SCP of the home PLMN. Okay, we have the 4 traces active here. Let's decode this TCP message first to be the HTTP to message. Okay, 4 traces are already. Let's get into the UEGNetB pod to execute this test script. This is the test configuration for this registration test work script. We have here the serving PLMN is for the home PLMN, and the PLMN configuration in The network function is the visited element. We have here also the connection to MongoDB database in the home element. Let's execute this test script. Okay, the test has been completed. And we can see here the result. The message has been appeared for the NGAP protocol and the HTTP2 protocol. So let's stop the trace. And let's filter it. And then save it to the new folder. Let's check. We have here the all four traces. Let's open these traces. Okay. We would like to check this message, the UE authentication data request from the EMF to the authentication server function in the home PLMN. So it will go through from EMF to SCP and the SEPP in the home PLMN, in the visited PLMN, and then go across to the home PLMN via SEPP, SCP, and then to the authentication server function. And then authentication server function will make query to the home PLMN UDM, and the UDM will make a query to the UDR. Okay, this registration test started with the registration request from the original B to the EMF of the visited PLMN. Once the EMF receives this request message, it will send the SBI message to the authentication server function for the UE authentication. You can see here from the EMF of the visited PLMN, it will go to the SCP of the visited PLMN. Let's check in the SCP of the visited PLMN. Okay, here we can find the message from the EMF to the SCP of the visited PLMN, and the same message will be routed to the SEPP of the visited PLMN. If we check the content of this message, this one, okay, this is the correct message, the EMF to the SCP, and then SCP will forward. Since this is UE authentication, we have here the message from the EMF to SCP. It sent the subscriber unique concealed identity and the serving network name. The subscriber unique concealed identity contains the home PLMN ID, and the serving network name is the visited PLMN. So the same message will be routed by SCP to SEPP. And then SEPP will forward this message to the SEPP of the home PLMN. We can see that in the SEPP home PLMN trace, the UE authentication. This one is the message that we are discussing. The same message that sent by the EMF of the visited PLMN. And then from the SEPP of the home file element, it will routed to the SCP of the home file element. So let's check. This is the trace of the home element SCP. This one is the UE authentication. So SCP send to the SCP, and SCP will forward this message, the same message, to the authentication server function. The same message that visited PLM and AMF has sent. Okay, once received this message, the authentication server function will make query to the UDM of the home PLMN. And then the UDM of home PLMN will receive this message via the SCP. And then the UDM of the home element will make a query to the UDR via the SCP. To the UDR, and then send the response back. And the contents is the authentication vector for this particular UE, containing the authentication methods, the permanent key, the sequence number, and the encrypted OPC key. So once received this response message, the UDM will forward this message to the authentication server function, and the message containing the authentication vector type, the random number, the authentication number, and the X result of this authentication, along with this authentication vector key. The authentication server function and then forward this authentication key to the AMF of the visited element via the SCP, and then SCP will send to SEPP of the home element, and then the SEP of the home element will send Let's see in the SEPP trace of the home PLMN. Okay, this one is the data, the authentication factor data for this UE, and then SEPP, once received this from SCP, will forward this authentication key to the SEPP of the visited PLMN. SEPP of the visited PLMN will forward this authentication key to SCP of the visited PLMN. You can see here the same data. The authentication factor, and then SCP of the visited PLMN will forward this to the AMF. The authentication fee. Okay, that's the authentication request and response message that sent across the visited PLMN to the home PLMN in this 5G roaming registration workflow test. This is the end of our video. I hope you can get the idea on how the 5G international roaming works between the visited and home PLMN using the Secure Edge Protection Proxy and the Service Communication Proxy node. Thanks for watching and see you in the next video.